So yeah, today I would like to talk a bit about the solubility and affinity. That could be done with MD, molecular dynamic simulations, and I will just have a small touch upon the COSMO software package. Now we're very limited so far experience, but still at least some conclusions we can draw already now, I guess, without some groundbreaking results, but rather general concepts that we can talk about. So first of all, I maybe should cover a bit the major problems in the drug delivery. And as far as I understand it so far, it's the solubility and permeability, and both are well treated from the experimental point of view, but there are of course limitations and complications, and sometimes it's costs, and sometimes it's lack of understanding of the nature of specific issues. So for example, with the solubility, we can perform, well, I guess in the simple case scenario, some shake flask experiment, and then analyze analyze our sample with the HPLC, and then it will show the peak at certain retention time. But if we're not satisfied with the solubility of that specific compound, that might be quite a bit of an issue to understand what exactly went wrong, why in that specific solvent our sample, felodipine or something else, it was not as soluble as we expected. So it's not clearly visible from the experiment sometimes. At the same time, we can also observe the structures. So what are they, for example, colloids formed in our samples? We can observe the structure with SACs or SANs, and then we also can visualize the actual picture with, for example, cryo-TEM or some other microscopy techniques. But again, even if we see the structure, even if we see some order, the regularity of that samples, it doesn't necessarily explain why and what's happening on the molecular level. That's where the molecular dynamics would step in, and maybe some other computational techniques, where we can actually go down to the very nanoscale and see what are those interactions, what are the affinities between the molecules, and what causes lower or higher solubility and permeability as well. But permeability, I think it will be mostly Shakavat covering the next week, and maybe Per as well. And we start with the, well, not really definition, but an example of solubility. A bit out of the standard pharmaceutical field, but still, I guess, pretty simple to just visualize. So if we have some salt that we throw into a glass of water, then of course, if it depends on the amount and depends on the temperature, but quite likely there will be some precipitant. So if we throw in enough salt, then some of it will be lying on the bottom of the glass. So basically what is happening is that these sodium chloride ion pairs, they will just stick to each other, and as long as the liquid, the solvent solution is already saturated, it won't really break by itself and start making new pairs, new interactions, and hydrogen bonds between the, let's say, sodium and the water, the oxygens of the water molecules. But if we put in some extra energy, if we, let's say, heat it up, if we microwave it, then the ion bonds will be broken. And then with a pretty high chance, these atoms the ions will be surrounded with the water molecules. So basically, this is already an example of the solubilization. So we put the compounds that we added to this, our solute that we added to the solution, in such a condition that it's surrounded by the solvent. And if you look at the diagram for that like schematic diagram for that process, we can see that along the course of the reaction, the energy overcomes some sort of a barrier. So initially that already dissolved to some extent, and that is already a stabilized solution. So we have supernatant, we have the precipitant on the bottom if we have enough salt. And in order to dissolve the rest of these crystalline structures that are lying on the bottom of the glass, we need to put some extra energy to overcome this barrier. And then it will be reaching that state where it's even lower, maybe lower. It actually also depends on the system. But in case of salt, it would get to a lower state and get fully dissolved. But if we now go back to a bit more pharmaceutical example, and this is the delta, basically. So we knowing that delta is the crucial part of more or less throughout our presentation, this discussion, that's the key part. So what's the difference between the energy states observed at different simulations or different experiments as well? So yes, back to the pharmaceutically relevant example. So if we have, for example, these, I think, felodipine molecules. So this is a crystalline structure observed from the Cambridge database. So as you can see, it's pretty nicely packed. And in order to take one of the molecules and solve it in the water, for example, we would need not only to basically to put some water in the middle, we just need to disintegrate the whole structure. And so first it comes as a smallest clusters and then single molecules. So, and yes, if we want to find out how it's related to the, how this change of the energy that we mentioned before is related to the solubility, that would be, again, this difference that is covered by the equation. So again, if we have this felodipine in this as a part of this crystalline structure, and if it's a quite hydrophobic drug, so it would be hard to pull it out, even if it sits on the surface, and it would involve at least three factors that would be involved. So first of all, dissociation from the crystalline structure. So how strong are the bonds between this molecule and the rest of the crystalline structure? To make the cavity in the solvent. So it depends rather on solvent and again on the interactions between this solute and the solvent to make space for it, for the molecule. And the third one is, yes, again, the interactions with the solvent. So once we already put it in this cavity, how much would be those interactions favorable or not for the system? And yes, to quantitatively describe this relation between the delta G, this is a Gibbs free energy, right? And the solubility. There's this relation. So basically, if we have a composition at two states, two phases, and where we have it dissolved and not, that will be proportional to the gas constant, temperature, and the logarithm of the partition coefficient. So basically, the ratio of the number densities in these two states. Yes, and this is more or less the key for most of the simulations that we are doing, the way we estimate the solubility of different compounds. So if we can see how the system energy, free energy, changes if we introduce this molecule, I mean, this is a simple case, and we will again get back to this later. Then after some sampling, we can see how this change of the energy, and that change of the energy will be directly related to how favorable this transformation or this reaction is when we introduce this molecule. So again, the same example, if we compare the two cases, one is, let's say, again, felodipine, and if it doesn't really want to be surrounded by the water molecules, it will, as much as possible, and on the next slide I will show what I mean by as much as possible, repel the surrounding water molecules. So it's a significantly lower or higher energetical state of that system in comparison to what it was before, because these water molecules are not happy. Now they kind of have to squeeze into some gaps, and they don't want to, if they overcome this barrier because of thermal fluctuations, if they jump in, this is already a bit of a molecular dynamics. So if on one step, after one MD step, it jumps in close enough to that velocity in some of the groups that are very hydrophobic, then the energy will rise very high, and that will lead to a less favorable energetical state. Another case is if you have the molecule that is attractive and attracted by the water molecules, so hydrophilic basically, then it still, yes, of course, it has some steric factor, so it might occupy some space, but these water molecules would rather come closer until they reach this, until their electronic clouds start to overlap. And yeah, this I will show on the next picture. But the point here is that basically in molecular dynamic simulations, we tune the parameters so that it's either our drug molecule or some other excipient or something, so that it would react either attractively or repulsively towards the other molecules, towards the solvent. And yes, a bit, just one slide of technical details here. So molecular dynamics basically is a method where we solve the Newton's equations of motion, integrate them. So let's say at some stage we have molecule A, which is blue, come close enough to molecule B, and these two atoms can see each other. Then it depends on these interactions, how most likely expressed via Lennard-Jones potential, how much they would like to stay in that position. If it's purely repulsive part that we just saw on the previous slide on the left, then this repulsive part will be dominating, and then the attraction is not as strong. And then basically these molecules will not really, they won't have attraction, but they will still have repulsion, and then they will avoid having the contacts with each other. And then if we extrapolate it a bit on the whole molecule or some clusters of molecules, it will also lead to phase separation. So basically, if there are more of the A molecules or B molecules, then they would rather stick to alike molecules than just have this repulsion that doesn't really contribute in any positive way to the minimization of the free energy of the system. I'm very sorry if I'm using the terms that are far from pharmacy, but again, I think that this is energy is quite a common term, so I hope it's fine. And then the the contributions here are the conservative forces, dissipative forces, where we have the friction and the speed, and the random force. So these two are related. Again, maybe I should not go deep into that, but by so-called dissipation fluctuation theorem. So if there is a lot of interactions and friction happening between the molecules, that is compensated, or that converts into the random noise. So how much fluctuations we have, so through the thermostat, so that the temperature of the system would kept the same. But again, back to the subject, that basically means that by tuning these interactions, so force field, this question we had yesterday, force field defines the strength of the interactions between these atoms. So this is a Lennard-Jones part. There's also electrostatic interactions, which is, of course, equally important, but I just didn't include it here. It's just a Coulomb mostly. Well, there are different forms, but again, that's generic form. But yes, if we just, in that equation, oh, no, I have no equation of Lennard-Jones interactions, but if we tune this epsilon in the standard Lennard-Jones 12-6 equation, then we will tune how much this the energy well is growing. So, and that is favorable for attraction, because this whole part is basically responsible for the attraction between two atoms. repulsion is for all types of atoms is very strong. So if we even increase this well a bit lower in just a couple of, well, let's say units, we won't go into details, the repulsion will be extremely high anyways. So it doesn't really matter if we increase it or not. So this is why this model is most common for molecular dynamics method interactions to describe those, the van der Waals forces. So, and yes, and so we know that if the molecules could be repulsive or attractive, we basically map these properties from experiments or from ab initio, from the first principles, on the actual force field, through the force fields on the actual molecules and the systems, and to see what is what's going to happen to the whole system if we put it all together. And then to measure the solubility, we would normally apply one of the few classes of methods, and the most common one is the free energy calculation. Free energy, basically we already discussed what it is, and if that could be applied for not only for solubility measurements, for instance, it could be also a ligand binding to protein, or yes, or mutation of a side chain as depicted here. Then what we would do is basically replacement, whether through some stages like here, or straight away if we just remove the molecule from a very homogeneous solvent, like from water, one single molecule, then we can just consider two states where we have the molecule and through maybe sub-steps for the convergence sake, but in general, again, the second configuration would be just the pure water. So where we would compare the free energies of these two systems. So, and yeah, I will go a bit deeper into details how that could be done, but the general concept is this. And again, this is a bit artificial system. This is a bit artificial operation in a way that, for example, there is no such phenomena in real life that the atoms would be just replaced to oxygen, or sorry, to hydrogen and then oxygen and then deform. So it's not happening this way. But for us, the main point is just to smoothly enough make a transition from one system of interest to another and see how the energy changes. So this is, in some cases, again, it's from one task to another, it varies, but it's necessary to not make it a dramatic change between the two. Okay, so one of the first methods here is the free energy perturbation. I guess one of the most common so far. Yes, this is more or less what I just mentioned before. So if initially we had the philodipine molecule somewhere in the middle of the box with water, then going through a number of steps, realistically that's 20 steps, I think, that is considered enough, we gradually reduce the interactions of this molecule with the surrounding water. So basically, I mean, when I say in 20 steps, I mean we run 20 simulations in parallel, most likely, where the interactions of electrostatic and van der Waals interactions of this molecule with the water will be multiplied by this lambda, which is, or yeah, 1 over lambda, or yeah, so where basically it makes this interactions weaker and weaker. And even though the water molecule is still here, the surrounding water molecules don't feel it at all. This is again necessary for the sake of convergence. We cannot just compare the two cases because it will be a bit random. Well, not a bit random value, but the uncertainty will be added to this system quite significantly, and maybe we won't get any result. But yes, the number of steps is necessary, and there are some papers about how many it should be and so on, but I guess this is already well established protocol that you can find in more or less any recent paper on that that uses the FEP. Yes, then the theory behind that method, I will try to use as few as possible equations, is that we basically compare the energies between the two neighboring states, so between lambda 0 and lambda 0.1 and so on, and yeah, multiply it by Boltzmann factor, and we get the free energy, here denoted with F. So, and that is one of the most straightforward relation, well, not relation, but pretty clear connection between what is in theory that we discussed and how it's done in practice. So basically, we just track the difference of the energies of the system where the phenolidipine molecule is present and when it's not. This whole method was first described by Zwanzig back in the middle of 20th century, but still one of the most popular ones. Yeah, here's another paper. So basically, in that paper, I have few of these recommendations along the presentation. If you want to start running some simulations with free energy perturbation, first of all, that would be maybe the first choice. And second, I would recommend to start reading with that paper. So there, if I'm not mistaken, predict the absolute solvation free energies of 239 small molecules of different nature. So I mean, they have, I think, basic, acidic, and the neutral molecules and different structural organizations. And their predictions are pretty well. And they use the OP-LS force field, and that is not something that we use in our lab, but still very common. Yes, so I would just recommend to start with using that. Oops. Yes, another method, also quite commonly used, but I would still say it's a bit less efficient and it's a bit more, it's a bit less flexible. So where we measure the solubility via the changes of the Hamiltonian with the same lambda change. So we go through several number of steps, and then not necessarily it will be just straightforward as with the molecule, I mean, as we assumed in the free energy perturbation. But so it might overcome several stages, or go through several stages through that development or evolution of this process. And yes, so Hamiltonian, which describes the system through basically describes the energy of the system through the coordinates and the velocities of all the particles. Its changes are tracked between each of the consecutive steps, and then the integral over those simulations over the average is taken. Again, the difference might not seem to be very clear between this method and the previous one, but it actually goes a bit deeper into equations. So I don't really want to go to spend too much time on that. So there are some mathematical formalisms, basically physical mathematical formalisms. But yeah, that is also very well known, and that is used in many software packages. So for example, in GROMACS, I think you can, well, maybe with some extra libraries as well, but I think by default you can use already both of them, thermodynamic integration and free energy perturbation. There are some papers again on, and even tutorials how to do that. Yeah, just in case if you're not familiar with GROMACS, this is one of these software packages that is mostly used for, at least in pharmaceutical field, for MD simulations. For both of these cases that I mentioned, it's quite important to have the correct thermodynamical cycle implemented. So basically, these are, I will have here two examples. this should all make sense. So we should not really skip some energy term that could be involved in the reaction that we are trying to describe. So for example, if we are looking at the salutation of the molecule, yeah, basically we want to dissolve it in water, then the energies in one part, so this the salutation energy, should be equal to the rest of that loop. So let's say if we now introduce the molecule to the system with the water, that the energy, that difference that would be caused by such an introduction of the or insertion of the molecule should be equal to these three steps where we have the difference between introducing our molecule of interest to vacuum and then water to vacuum, and then from water in vacuum towards the system again where we have both water and molecule, and yes, and this initial molecule that we want to dissolve. So basically here, as if we have just one water molecule in vacuum and then we leave just vacuum, the energy will be neglected, and that's why we would have this just these two terms. Another example of the same thing, if we want to compare how well, how strongly or how big is the difference between the interaction of this I guess receptor and ligand, is it here? So anyways, between the particle A and the bigger molecule or the solvent, and we have the other one, alternatively, like this B molecule, a particle. Yes, we can either replace one with another or go the full cycle, but these two should be equal to each other. So if we just remove it first, then, well, this one is the same basically, and then we introduce the B molecule. So basically, in other words, if we just replace one molecule with another as a transformation, that should be equal to removing one molecule and inserting another molecule. Yes, and I mean, again, these are just some simple examples, but in once someone is running the this free energy calculation with actual replacement or modification of side chains or something, then it all makes big sense to be careful with intermediate steps. Yes, another paper. This one is for thermodynamic integration, and yeah, as I said, it's also quite one of the most used methods and maybe easiest to understand in terms of the equation if you need to go through all of it. And here the authors compare, first of all, they compare the performance of several numerical integration techniques. So basically, if you remember these several points that we had on the graph, we still have to interpolate between those. And it actually depends a lot. So how precise we're gonna be in our with our final results, how well we interpolate those. So if we use this what's the trapezoidal, I guess, interpolation, and then Simpson's method and some others. So it will all contribute quite a lot. So these guys in that paper, they not only cover a lot of basics of thermodynamic integration and have some interesting results, but also have few steps aside from that subject, and they compare it the results with different sub methods. But even better, well, for me personally, even more interesting paper in that regard is that one by David Mobley and co-authors, where they also not only they introduced this, not only they had quite a good analysis of several solubilities, but they came up with a software. It's basically, I think, a Python script somewhere on GitHub, but it's of course referred to from the paper, where one can easily run all the analysis routines. So with all these methods, with Bennett, also other ones that I haven't mentioned before, Bennett acceptance ratio and multi-parameter, I think, Bennett acceptance ratio, and also this TI and FEP, which is exp as well. It's the same thing. So basically, you can compare those. You can see which one is working better, and that is often quite important if you really target in some specific group. So there might be some specificity that determines the quality of the results you're getting. So this, I think, is a very useful paper. And again, it covers the difference between the methods a bit. So it's maybe good to start if you want to do some tests. Another thing that could be done with the simulations, we can study the molecule partitioning if we have the two immiscible solvents. So like here, it's, for example, water and octanol. Then, well, I guess you all know how important it is to know what's the partition, what's the log P, how much it's dissolvable in one media in comparison to another. So whether it's more hydrophilic or lipophilic, and that basically causes the whole difference in how we would use this drug and what would be the formulations, enabling formulations that we could apply. So this also could be done with the molecular dynamic simulations. So specifically, well, yeah, this picture is just taken on the interface of these two media, and we can see how much time this molecule spends in one media or another, or to which extent it's in the left part or on the right part. But more quantitatively, it would be correct to measure the free energy with, for example, free energy perturbation, so one of the two that we mentioned before, or also thermodynamic integration. So in combination with one of those techniques, we could measure how the free energy of the system would change if we introduce this drug molecule into water, into octanol, and then take the difference and divide it by this factor of 2.3 in Gauss constant and temperature. And then we would get the log P. And that is, I would say, quite accurate, but again, depending on the system, depending on what are the solvents that we are looking at. And yes, this was also based on the free energy calculations. Widom insertion method is a bit of an alternative, so still not that different in terms of how it could be realized using some, well, common software packages, but different in its concept. So here it was first suggested by Widom again also in the beginning of 20th century. The drug molecule, or whatever the molecule of our interest, should be inserted into all possible spaces inside the simulation box, and then the energy of the change should be measured. So I mean, we just gradually, one by one, insert our molecule, again, maybe felodipine, into all the possible spots within the box and measure how the system energy would change. So it's rather a statistical approach. So we just would see how in average that would change. And yes, here, this is the chemical potential, and it's proportional to the average of the ensemble average of the yes, this exponential factor with the interaction energy of this randomly placed molecule that we try to insert in different places. Well, I mean, it's quite interesting, but most commonly the problem is that if our molecule is big, then it would be very hard to squeeze it in anywhere. So even though, yes, the energy would be huge and so on, even for a smaller one, but still that one would be a bit harder to organize, at least, again, from very limited experience from us. Yes, well, I don't know if you already got this question, but in all the previous examples, we were talking about the energy difference, right? So it doesn't tell you directly what's the solubility of that specific drug. And there are two answers, basically. One, we will again get back to this when we go to Cosmo, and another one is here that you would need to have a relative, so you would need to have experimentally known value, and then, or maybe the set of these experimentally known values, and then if you measure those, and then if you measure some extra compounds, you can map it on that known value scale and see how soluble that should be in comparison to those. And this approach is pretty well described in that paper, also by David Mobley. He is actually pretty big in that field, specifically in the solubility with MD. And yes, so there specifically, they put the same solute into different solvents. And yes, you can then scale it. In the same way, it could be done other way around. So maybe one have a number of compounds that could be dissolved into this in the same solvent. Then again, it could be tracked. So one or another way, once you have some reference data that is quite reliable, that will work. The only issue is that if we work with very poorly soluble drugs, then quite likely it will be still hard, because if you look at the databases, or even if you try to perform this experiment by yourself, how soluble is very poorly soluble drugs, the variability will be very high. And yeah, the discrepancy, the variation between these sources would be also very high. So it's hard to pick something that you could really use as a solid basis for that. But once you do that, that of course works very well. Another concept, well, still very similar, it's also in relation to another reference, but here it would be just the ideal solution that we would consider as the reference. So in ideal solvent. And that would be taken as something that we would compare all our other solubilities to. And this is also described in another David Mobley and a few other coworkers' paper that I would also recommend as well. Yeah, and so if we do it all with these relative solubilities, I mean, basically we can just study some small pieces of the whole picture, right? So basically, if we have one molecule in one solvent and then another molecule in the very same solvent, it's all very interesting. We would understand how differently they interact with that solvent. But in most cases, the whole picture in, let's say, intestinal fluid or gastric fluid, it's many different things. And the variability is also very high in composition of those. I mean, if we just consider 5 or 10 nanometers scale box, then it could be anything between those. Of course, in average, we could know that, but the solubility values would differ quite significantly. So in ideal world, I would be interested to see how several steps. So first of all, if the molecule would dissociate from the crystalline structure, it could go backwards. So it would be good to know what's the affinity of the molecule to itself. So that's one part to measure in ideal setup of computational experiment. Another part would be if we assume that this single drug molecule made the whole way to the membrane, whether it's gonna get inside and whether it will permeate through the membrane. And what would be the energy for that? How favorable is that interaction, even if it makes the whole way? We also need to know actually what's the probability to reach the membrane. And the last scenario is, which is actually many sub-scenarios, if this drug molecule from the crystalline structure, it will attach to some colloidal structure. For example, in intestinal fluid, there are these bile salts and phospholipid that make micelles and vesicles, and so it might whether sit on the surface or it might go in the center of the micelle. So for one specific molecule, the API, if we take it, if we consider all these different steps, and then we also study how that molecule would, how likely it would go from the micelle to the membrane when the micelle sits. Again, there might be different phenomena here. It might be a fusion or endocytosis or something, but still, if we actually want to study the whole concept, if we want to understand how the solubility works, the whole chain from the crystalline structure to the blood, then there would be a number of pieces to put together. And then if we know these probabilities, what's happening, how likely that scenario with the clustering with other solutes happening, what's the chance to get straight to the cell membrane. So if we have all these probabilities together, and if we know the free energy profiles, then we can actually, if we can automatize this process, then that would be a very interesting workflow to basically analyze and predict fully what's going to happen in a complex environment. But today, I think it's practically not feasible. So that's why we limit ourselves to just comparing the solubility of compounds in different solvents, or other way around, several compounds in the same solvent. Another thing I wanted to cover is this affinity, and specifically an example of the amorphous formulation. So we did with a colleague from drug delivery group, we did this computational study. So she did the experimental part where she had this drug that was amorphosized. So basically made a powder, or smaller granules. But then the problem with these amorphous solid dispersion formulations is that it's not stable. So it tends to crystallize backwards, more or less what we observed. So even if it's not within already the liquid, it's rather in the storage room somewhere, it would tend to form again this sort of semi-crystalline structure where it would be less soluble. So that is done to make it more soluble, but if you leave it for a long while, then it will get back to this, or at least to something similar to the solid structure. For that purpose, there are several techniques how it could be modified, or how it could be stabilized, and one of them is introduction of the polymer. So we used HPMCIS. I unfortunately cannot pronounce what it stands for, but this is also quite common in the field. So here, if we add this polymer, then quite likely it will prevent the aggregation of the, if we mix it with a polymer, it will prevent the fast aggregation and crystallization. So basically what you can do from MD point of view, from molecular dynamics point of view, you can just simulate the mixture of these drugs with polymer in one case. So it would be a dry system, and you could have it humid if you introduce some water, whether on the top or mixed with everything, and then see what are actually those processes, what is happening, how the polymer helps. So first, visually analyze that, and second, there are some quantification ways as well. So this is the one monomer of our polymer. This, I guess, is how it looks, several monomers together, but actually it was longer than that. So I just want to first show you a small example of how it looked like. So for two different drugs, propofol is much more hydrophobic. So it really tends to get away from water as much as possible. Here, the process included several stages. First, we warmed up the system until it reached 550 kelvins, so that it would actually become melt, so all the molecules could be mixed, polymer and water and API, because otherwise it tends to phase separate from the very beginning and nothing happens at the room temperature, at least on the scale of nanoseconds and up to microsecond. But if we raise the temperature and then gradually decrease it, so sort of anneal to first lower and then back to room temperature, then we will actually see what we assume, that we will actually see what's happening on the longer term perspective. So we would speed up the simulation in a way. And you can see here that for this highly hydrophobic drug, propofol, which is represented here by this whitish color, it tends to make one cluster, which maybe has some contacts with water, but mostly there is this polymer which serves as a buffer between the two. Yes, and another example is sulfamyrazine, where this molecule actually is, it has a smaller, if I'm not mixing up, log P. So basically it's happy to mix with polymer, it's happy to mix with water, and it's happy to mix with itself. So it won't, even after the whole same procedure that we discussed before, it won't really phase separate, and you can see that it's pretty well mixed. And if we look at the experimental results and we match what we observed from the MD point of view, we can already have some insights on what is actually happening. So we see the values from experiments, which one is more stabilized with polymer, which one is less, and looking into that scale, we can understand what is happening. But speaking specifically about the affinity, that would be the chi calculation. Chi stands here for, it describes the miscibility of the system. It comes from the Flory-Huggins theory, or Flory-Huggins parameter is another name for that. So basically, here one needs to take a look at the cohesion energy of each compound. So if, let's say, we have the dry system of polymer and drugs that are mixed, we get one energy. Then if we have only the polymer system, if we have the API system, and then we have also these molecules taken from these systems one by one and put into vacuum, and then their energy measured. So basically, in such way, by just some sort of arithmetical operations, we find out what is the change of the energy that comes in when we put all the molecules together. And this is characterizing the miscibility. In few words, this is how I could say that. So basically, if we measure the energy of this molecule in vacuum, and then of the same molecule in the same configuration, but when it's surrounded by the rest of the molecules in both pure API mixed system, and we do the same for polymer, we put it all together, multiply by the molar fractions, and then normalize by the volume, then we get this chi, which is, well, the interesting interval is basically between 0 and 0.5. So if it's lower than 0, then the interactions are supposed to be, so it will, okay, I might again mix that too, always mixing that. So if it goes higher than 0.5, I think the system will definitely phase separate. If it goes lower than 0, then it will quite likely be well mixed. So these are the values that could be measured relatively easy, but again, that would require a lot of small, relatively short simulations. But this is something we do. Another thing that could be measured from such simulations is, for example, RMSF. So how mobile these molecules are in this equilibrated state. So how much they can move within some, what's the radius and so on. I mean, yeah, well, not really radius, but the displacement from the average position. We can calculate the number of hydrogen bonds formed. So we can measure it along the evolution, along the change of the conformation, or in the final state, we can compare it between different drugs and so on, and we can analyze what's the nature of the interactions of specific polymer with these drugs, and why this polymer stabilizes one drug better than another. And finally, yes, radial distribution function, which is similar to structure factor, which is similar to several other things. And again, miscibility, it represents how the molecules of one type can sit around the molecules of another type, or not necessarily the centers of mass, but also specific groups. So how much the drug, this sulfamyrazine, tends to sit around some of the groups of the polymer that we had. So this whole analysis could be performed pretty easily. And yeah, this is how it typically looks like. Yeah, I'll skip it. Another thing, actually, I just wanted to mention that we already, within this Nordic POP, we had the collaboration with Corby from Copenhagen University. So basically, he provided some data, and I mean, most of it is available also already published, how proteins can stabilize the amorphous formulations. And so this we can also do. Here comes a bit more uncertainty with how precise we are with the introduction of the proteins. And then again, we still have to make some assumptions. We need to heat up the system. And basically, you can't really heat up the proteins in real life to up to 550 kelvins. But again, with some assumptions, we know that in simulation, that is a bit different scale. And that really just speeds it up, but it doesn't really change the conformation. And of course, we can introduce some or reduce the number of degrees of freedom. So basically restrict some parts of the protein so that it wouldn't change conformation. So, and this was also analyzed how these drug molecules would move and how they would interact with the protein. So finally, I would just in maybe a few minutes talk about the COSMO. So COSMO is a commercial package, pretty well known again in the field. I think many groups are using this. There are many papers coming out, but there are still also some limitations. So it's meant to be used mostly for solubility predictions, also log P and density, pressure, many things. Yeah, I guess solubility is one of those mostly reported in papers. Yes, COSMOtherm is a bit more advanced. So there it calculates a bit more thoroughly the whole system, and you're supposed to get a more precise result. But there at the same time, you can introduce some molecules with a pretty high precision of your choice. Whereas this COSMOquick, it can also produce the structures if you provide a smile string, but at the same time, it's way more generic. So it doesn't really, it's not supposed to be used for some precise results, but sometimes it's very good for pre-screening. So one can use it to find out whether one drug is more likely to be better soluble in that liquid, in that solvent. So this also has advantages. So this is quick. This is a bit more advanced, but at the same time, more precise. Yeah, this is graphical interface. So there are quite a number of things you can do here with phase diagrams and so on. Yeah, you can also study how it interacts with micelles and how permeable some molecules could be through, for example, membrane. And the workflow means that if you need a prediction of, let's say, solubility, then you would need to have the COSMO files, which there is a pretty big database. I think it's 20,000 molecules, but to be honest, it's still very limited. So, I mean, if you have some new drug or something not well studied, then quite likely you will have to produce these files. And then either you use TurboMol, which is another software from the same company, from Dassault Systems, and then you can produce it. You can produce the COSMO files, or you can use alternatives such as Gaussian, for example. So we are now currently trying to use it with Gaussian. So it will also do the DFT calculations, the quantum chemistry calculations, and produce these COSMO files, which that after all could be used for COSMO, and then the prediction could be made. But given the fact that one would need a number of conformations, if you have a pretty big molecule, for me, pretty big started with I think 80 atoms. So it already starts to be a bit messy to produce this COSMO file and multiple conformations because yeah, well, it requires a lot of resources. And after all, again, one conformation doesn't really represent anything. So you really should go over many of those and pick some representatives from each group of configurations. You don't really want to fit thousands of them. Here, there is a plus if you're using the TurboMol, then you can also use the COSMOconf, which will pick the right conformation. So you need still to run your molecular dynamic simulations where the molecule of interest is changing, is moving, and so the angles are changing, and then feed it into the COSMOconf with the support of TurboMol, and it will produce the most relevant configurations. Then it all will be put together, and the solubility would be measured. Yes, so there are, as I said, it might be quite intense, but at the same time, it's very user-friendly. So if you can produce the trajectory with molecular dynamics, you will definitely be able to use the whole package. But it's much easier if you use all the products from the same company, not with Gaussian, for example. So I think with that, I will stop here, and thank you for your attention. And if you have any questions, I would like to try to answer those.